Welcome to this lecture about evaporative cooling and the use of environmental cold for passive cooling. This will be our second and last lecture about cooling systems. Water vapor condenses at 100 degrees Celsius at atmospheric pressure, as we all know. But what happens if this water vapor is mixed with air, like happens in reality? The air is humid, we say, meaning that it is not pure air that we are living in, but a mixture of air and water vapor in different quantities depending on season and climate. Let's take a volume of air at atmospheric pressure, 1 bar. If there is pure air, the pressure of the air is 1 bar. If it is mixed with water vapor, this water vapor takes a certain place in the volume, and this is reflected in what we call the partial pressure. The less water vapor, the lower its partial pressure, and the higher the one of the air. You see in this graphic the partial water vapor pressure corresponding to a certain quantity of water vapor in 1 kilogram air. Also, when the air feels very humid, the absolute content of water remains low. See here, it varies from 0 gram, completely dry air, to 20 gram per kilogram dry air, which will feel extremely humid at high temperatures. On the vertical axis, you see the partial pressure of the water vapor. Of course, it is very low, as there is in fact little water vapor. If you now remember the boiling curve of water, you see that at these very low pressures, water can boil and condensate at temperatures much lower than 100 degrees, meaning that at room temperature or outdoor temperature, water will evaporate already. And you also have learned that when a fluid is evaporating, it takes a lot of heat from its environment. So if you inject water droplets in air, it will automatically evaporate because of the low partial pressure, and by evaporating, it will take its needed latent heat of evaporation from the air, which of course will cool down. That is the principle on which evaporative cooling is based. There is a limitation to this, which is the temperature of the air. Depending on this temperature, there is a maximum of water vapor that can be included into the air. When this maximum is achieved, the air is said to be saturated and cannot absorb any more water vapor. For instance, at 20 degrees, air cannot absorb more than 7 grams of water per kilogram air. Imagine that we inject 5 grams of water droplets in dry air at 25 degrees. The partial pressure of water vapor is then 0.08. At this pressure, the latent heat of evaporation of water, which is shown in the right figure, is 2488 kilojoules per kilogram. As we have 5 grams, we have to multiply this latent heat by 0.005, which gives 12.4 kilojoules. This heat is taken from the air, which will then cool down using the well-known formula Q is mCp delta T. M is 1 kilogram, or to be precise 0.995, but we round it to 1. Cp of air is 1 kilojoule per kilogram Kelvin, so delta T must be 12.4 divided by 1 times 1, which is 12.4 degrees. So, the final temperature of the air will be 25 minus 12.4, which is 12.6 degrees Celsius. This gives a huge potential for cooling and costs no energy. Of course, the efficiency of the process is not 100%. Some droplets may not vaporize. It is generally assumed that the efficiency of vaporization is somewhere between 60 and 80%, meaning that much more water is needed than the 5 grams we just discussed in the example. And of course, we need a pump to pump the water and spray it in the air. And in air handling units, we also need a fan to circulate the air. You see here a few examples of evaporative cooling. Left a very simple, not very effective home system with just a water container and a small fan. Then a mist machine, often used outdoor to cool a bit hot warm outdoor air. Then in the middle, a picture of a wind catcher in Iran. When used in combination with a fountain or a spray, see both figures below, it is quite effective in cooling warm, dry air. The last picture shows how it looks like in a simple air handling unit. The air is forced along the sprayers and is cooled this way. What about the pump power? Well, it all depends on the water flow rates and the water pipe design, but it is a very small amount of energy in comparison to the cooling power. Evaporative cooling is very efficient in terms of energy usage, and we can by approximation neglect the energy use of the pumps. However, it is not applicable in humid countries, as the air there is already close to saturation. Be also aware of a potential danger of evaporative cooling. As the water has a low temperature, it may contain the Legionella bacteria that can cause serious lung infections. It is therefore important to regularly heat the water tank above 60 degrees for a few minutes or to use chemical disinfectants like chlorine. Let's now study the possibilities offered by passive cooling, fully based on the use of environmental cold. In many cold and moderate countries, it happens that there is already a cooling need while the outdoor temperature is lower than the indoor one. This can happen when there are a lot of solar gains and when the internal heat load is high. Think of a meeting room or a classroom, for instance. In this case, additional ventilation with outdoor air will help cooling the building. How much cooling this can bring depends on the energy balance and was studied in the course Energy Demand in Buildings. All over the world, nights are generally cooler than days. In the course Energy Demand in Buildings, we touched on the fact that buildings retain a lot of heat in their construction. In heavy constructions like concrete walls, the building will hardly have time to cool during night, so the temperature in the morning will be already warm and will keep increasing during daytime because of solar radiation and occupancy. It is therefore an efficient strategy to try to cool the construction as much as possible during night by ventilating the building with cold night air. This way, the construction walls will be cooler in the morning and the temperature during day will be lower. Making estimates of how much cooling can be gained this way is beyond the scope of this course and will be handled in another course for advanced thermal simulation. Let's look now at the potential of the ground. In general, the shallow ground is colder than outdoor air during the hot season. There are therefore passive systems making use of this by circulating the outdoor ventilation air through pipes in the ground, so-called earth tubes. The air is then cooled by the ground. Similar systems are used by having the air circulating in a cool basement, for instance. It is important to take care that pipes and basement are clean and that no condensation occurs to maintain a high air quality. If the pipe becomes humid, because the water vapor condensates on its surface, it can facilitate mold growth and the air can smell stuffy. As for the sizing of these pipes, which may need quite some length, it is all about the conduction heat transfer between the pipe and the ground and the convection heat transfer in the pipe. These estimations are beyond the scope of the course. And what about the use of surface water? Surface water may be a pond, a river, a lake, or the sea. Their temperature is generally lower than the outdoor air temperature during summer. For instance, river water can be used to cool indoor air using a heat exchanger. The warm air needs to be brought along the heat exchanger using a duct. The cooling power depends, of course, on the temperature of the water. The colder the water, the more heat can be exchanged. In many countries, there are regulations about the maximum temperature at which the water is re-injected into the river, lake, or sea. This maximum temperature is around 25 degrees Celsius or even lower, limiting this way the available power. The aim is to protect the fauna and flora in the water, which could be harmed by too high temperatures. This system is not completely free of electricity, as a pump is needed to pump the water through the heat exchanger, and a fan is needed to circulate the air. By the way, this system may also be connected to a water system for floor or ceiling cooling instead of being connected to air. By using the simple equation Q is mass flow rate times specific heat of water times delta T, it is relatively easy to make estimates of the needed water flow rate and the available power. When it comes to the primary energy and CO2 equivalent emissions of evaporative and passive cooling systems, we can state that they use very little energy in comparison with others. They need only pump and fan energy. We will consider that by approximation their primary energy use and CO2 emissions are very close to zero. But for more accurate estimations, we surely should calculate these pumps and fans' energy usage. This lecture was about evaporative and passive cooling. Passive cooling uses very little energy, only pumps and fans are needed. You have discovered how evaporative cooling works, and you can make simple estimates of its cooling power. You are aware of different types of applications, including applications in air handling units. You also had a look to other techniques like night cooling, earth tubes, and the direct use of surface water to cool air. Thank you for your attention.